I'm going to be
All right. Okay, it is time, so we're going to get started. I found a really kind of cool program. It's called TK Gate. Does anyone know what it is? The TK Gate. TK is a programming language. TK Tickle, TK TCL. So anyway, I will show it to you guys because I think some of you may find it interesting, especially those of you who want to become a software. I mean, not a software, but computer engineer, or in EE, working with digital circuits or gate level type of specification. So you might find this one useful. It's not as boring as Verilog and VHDL, which are text description languages to specify gates, so you can actually design your own processor. This one is more GUI based. You can actually place the gate and draw the lines and stuff like that. I'm not going to require you guys to do it as a homework assignment because I'm pretty sure that most of you will have to install quite a bit of software to get TK, the programming language TK to work on in Windows, because you have to install SysWin, and then within SysWin you have to install Xwindow in order to get this to work. But in Linux it's easy. After you install TK Gate and you're done. Okay, but I will show it to you today because we talked about how to add numbers. Remember, we converted arithmetic operation into logic operation, into gate specific, into gate logic. So we'll revisit that first today, and then I'll go ahead and show you, what it looks like when they're turned into actual, gate logic. So I'm going to use mousepad here as my, quick and easy, whiteboard. So it will be captured by my recorder. Okay, so we'll just go ahead and quickly revisit what we went over on the other day. 0 plus 0 is, the result is 0 with a carry of 0. Is that okay so far? So I'm going to make these 4 rules because with 2 inputs, we can end up with 4 results. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. The only time we actually have a carry is 1 plus 1, which is 0, but with a carry. Okay, so we went over this last time, and these results are based on the definition, the arithmetic definitions of addition and also carry. So are there any questions at this point? And obviously these are all base 2 binary arithmetics, not base 10. So we still do okay so far with the arithmetic definition of addition, but in binary. Okay. So now we move on and talk about the gate logic that we can use to specify this. In order for the carry to be a 1, the only time when it is a 1 is when both inputs, the number that you're adding, are also 1s. And in all the other 3 cases, the result is a 0. So it's pretty handy to find a gate to do that. Okay, can someone remind me what gate would do exactly that? What logical operator would do exactly that? The AND gate. Okay, the conjunction AND gate. Okay, so that means the carry flag can be expressed as, if I look at these 2 numbers here, as A plus B being the input. This is my result, and the carry is C carry itself. So in this case, I can re-express C, which is the carry of a binary addition, as A and B. It will serve exactly the same purpose. It will get me to the right result. Is that okay? The one that is slightly more difficult is the result, okay, the actual result of the addition. And I think last time we talked about this too. So the result itself can still be expressed, but not a very simple one, because what it looks like is the negation of A or B without the negation, and B without the negation, or A and not B. Like that. If you want extra parentheses, you can put extra parentheses around the negation, because the negation only affects whatever is right immediately after that. Okay, so that should make it extra clear, which operator is operating on which input. So I'm hoping that most people still kind of remember this part from the lecture last Thursday. Are we still doing okay so far? The symbol that I used to represent the numbers may not be exactly the same, but it's close. Okay. So what we want to do now is to, remember last time I talked about jelly bean logic, 74HC type of logic, and you can use a breadboard, hook up everything, and then actually see the addition happen. I kind of mentioned that, I'm not sure how many people understood what I meant by jelly bean parts, 74HC, ICs and stuff like that. They're getting pretty obsolete by today's standard because nobody actually needs to use jelly bean logic anymore. We have programmable logic like CPLDs and FPGAs and stuff like that are field programmable, and so we don't need to solder parts that are not programmable onto circuit boards anymore. But anyway, let's see what it looks like when we actually create this as a circuit using gates. And I have it already pre-made because I don't want to spend class time to actually do it. So I'm going to run this part here and go to my cisp310 folder. And the program that I use is called TK-Gate. The latest Debian Live image has this program pre-installed. So for those of you who are using my ISO image, you just have to re-download it, rerun it onto your USB drive, and you have this program already installed. If you're using the virtual machine, don't bother to install it because it won't run in text mode. Okay? You can install it, but it's going to suck in a lot of packages. And I don't think the virtual machine, this image is large enough to accommodate that. So you may not want to do that if you're using the virtual machine. Okay, so now I'm gonna run the program, TK-Gate, kind of cute. So this is the overall picture for the gate logic that I was talking about. So let me just position this right and zoom it in at the right level, like so. Okay, so I have two full adders in this case. I have the first bit per column has the input from this switch here and also from this switch here. So these two switches are basically zeros and ones as input into the full adder. Okay, so that's a full adder. There's no carry coming from a digit of a lesser significance because this is the least significant bit. And then on the other side, on this side, we have another full adder here. It's taking the output of the carry of the previous adder into the input here. It also has its own number here. This is another digit here. This is the most significant bit. There are only 2 bits here anyway. And this is also the most significant bit of the second number. The output are here. These are LEDs. So this is the output of the first bit. This is the output of the second bit. This is what we call the carry flag. In other words, if the resulting value cannot be represented by 2 bits, that carry flag will tell me that the result cannot be represented using only 2 bits. Okay, it's just kind of like when you perform 2-digit by 2-digit addition in base 10, sometimes you end up with a number that is larger than 99. Okay, so that's basically a digit that cannot be represented using only 2 bits. Are we kind of doing okay so far? I can show you what is inside the full adder. So inside each full adder, is a half adder. So I can show you what is inside the full adder. So inside the full adder, it looks like this. We have A and B serving as input. C in is also an input. C in is coming in from the carry of the less significant digit. A and B are the input of this particular column when you're doing the binary addition. The output, on the other hand, is right here. We have R here as the result of that column, and then we have C out as the carry to go to the next bit. But nothing like this. We still haven't seen the logic that we were talking about earlier, which is this part here. We still haven't seen A and B. We haven't seen the negation of A and B or A and the negation of B. That's because that logic is only used to specify a half adder, not a full adder. This is a full adder. It's made up of 2 half adders. Each box is a half adder. So if I look into a half adder, then we actually get to see the gate that we were talking about earlier. And I can afford to zoom in one more time, just because this is a smaller picture. And here we have it. So once again, A and B are the input, and this one is consistent with the text representation. Let me display both side by side so you can actually see the graphical representation of the gate logic that is in text originally. Okay. Are there any questions at this point before I continue to talk about the gate logic? Yeah, go ahead.
Is it called which element, which is and, which is for?
Say again?
Which element, logical element, represent which operator, or and then?
Okay, that's a good question. Well, if you look at the original text representation, we have 3 AND operations, right? So when you look at the graphical representation, which symbol happened 3 times? Yep, it's the one that has a straight line instead of a curved end. So that's an AND gate. The one that has a curved end, which is this one here, is an OR gate. The little bubble on top of the AND gate, that's a negation. That's a negation. The bubble represents a negation. So when you follow the wires, you can see that A goes into the first conjunction without negation. So this conjunction or AND gate is representing the second part of the disjunction. And then when you look at this gate here, it is taking the non-negated version of B, which means it's taking this side here. But A is also, if you just follow the line here, it's also going into here. So that means A is negated before we get into this AND gate here. And that means, it's this side of the disjunction. And this one has B going here and then go to here. But before it gets into the AND gate, it is negated. So that's why, this gate here is represented in text by this portion of the logical expression. Are we doing okay so far with this picture? Okay. What about the OR gate? Well, the OR gate is happening on the outside. It's taking the results of the conjunctions and combining both conjunctions into one single output. So that OR gate would be this guy here, because it's taking the output of this conjunction, taking the output of this conjunction, and combining that using a disjunction into the output that we call R here. And I use the same symbol R in the circuit diagram. Is that okay? All right. And on top of this, we have another gate, that is going to output the carry flag, which is a very simple conjunction, an AND gate, because it's just taking A. If you follow the wire here, it's taking A, which is not negated. It's taking B, which is also not negated in this case, and create the output here. It is corresponding to this expression that defines the carry flag. Yep, go ahead.
So the small little square just means it can flow in any directions at that moment.
No, the little bubble means, are you referring to?
No, squares.
Squares.
The
squares are junctions. Yes.
Yes.
So without a square, the wires are flying over. But with a square, it is a junction, which means it is a distribution point. Yep.
Is there a way piece of hardware, like AND gates? It's actually a transistor. Gates.
Right.
Is that actually AND gates combined?
When you're actually getting down to the silicon of a processor, there are preferred gate types. So I think NAND or NOR, one of those two, is a preferred gate type. But from the given primitive gate type, you can actually create all of the other gates. So as far as we are concerned, it's okay to express it like this, because you can take this and the compiler, quote unquote compiler, can compile this into the preferred gate type and do it in an efficient way. But this makes it easier for us to understand. That's a good question. All right, so this is the quote-unquote microscopic view, and if I use an example to illustrate it, okay, so let's take a look at an example here. Let's say we have 2-bit by 2-bit addition, so I can relate what this is actually doing. So we have So okay, this is A1, this is A0. So A is a number. A1 is representing the most significant bit of the number A. A0 is representing the least significant bit of the number A. And then we have B1 and B0 here. And let's perform an addition. Okay. So according to the convention, of what we observed last time, if I call this, we'll call this R0, okay? And we'll call this R1. We'll call this, C1. We'll call this, C0. And obviously, we use R already. We'll call this S1 and S0. Okay, here we go. So now the question is, how do we get to R0? Well, R0 is just the output of a half adder. Is that okay so far? In other words, if A0 is here, B0 is the input of this entire thing, the output of this entire thing is R0, which appears here. If this is A1, this is B1, the output here is actually our R1. And we are missing something here. We're missing a C2. So C2 is actually this guy here. If A1 is this input, B1 is this input, this C is actually C2 because it is a carry to the more significant digit column. Are we still doing okay? Kind of? Okay. So, and that's why it's called a half adder, because with this logic here, with this picture, it can only handle this bit plus this bit, making this result R1, R0 here, and making this C1 over here. It's a half adder because it only completes one half of the addition of each column when you perform bitwise addition. What about the other half? Well, since it's a half adder, we just have to add another half adder to make a full adder. So the other half adder is going to take R0 as A, take C0 as B. Those are the input into the other half of the full adder. The output becomes S0. This R becomes S0 because that's the actual output of the entire thing. The carry from this addition, C, becomes C1 also. So that means we have two ways to contribute to the carry of the next digit, because it can happen from the first half adder, for the first half of the addition, or the second half of the addition. So the carry to the next bit can come from one or the other source. So now the question is, how do we combine those two? If we look at a full adder, now remember this picture, okay? This is the picture of a half adder. When you look at a picture of a full adder, this is what it looks like. And I cannot display the entire thing without zooming out just one bit. Okay, so zooming out just one bit, this is the picture of a full adder. Each box is a half adder. So we have, A as the input, B as the input. Let me display the text on the side here, so we can, this way it's easier to see it. This whole thing represents one column of the binary addition. A is A0, B is B0. The output, R here, is our S0. And C out is C1, which is the carry bit to the next digit. Are we doing okay so far? But you can see that each half adder is contributing a carry. So now we have two outputs, from each one from each half adder, and we have to combine them into one single output for the carry. And you can see how we combine those two. The carry of the first half adder, which is adding these two guys, is coming into the OR gate on the left-hand side. The other carry, which is the result, the carry from adding this bit to this bit, is coming in as the right-hand side of the disjunction or the OR gate, and the output becomes the actual output of the carry, which is fed into this part here. So that means we can have a 1 as a carry from either addition into the next digit. Are we doing okay so far with this? kind of. Now you can come back and revisit this. I can make this code, available to everybody. So if you're running Linux, as a virtual machine or otherwise, you can actually, run it and see what happens. And you can also extend it if you want to. So this is a full adder, but it's only good for one column. And if I want to have 2-bit, adding 2-bit, I need something like this, because I need 2 full adders like this. And let me once again show the code on the side here. So this is representing, the text is actually representing this entire thing. We have 4 inputs, because we have A0, B0, representing these 2 bits, A1, B1, representing these 2 bits. As far as the output is concerned, this R is S0, this R is S1, and this C out is a carry that is floating somewhere, because we can only represent using 2 bits, is actually this C2. What about the carry C0? Well, because it is already the least significant bit, we use a ground, which is equivalent to a 0, as the input into the first carry, or the least significant full adder. And that completes the entire circuit. Are we okay so far with the concept? At least, just focus on the main concept first. Okay, we are now implementing addition in binary, not using arithmetic operations, but using logical operations, booleans, okay, gate logic. And that's the most important part of this lecture is, we are converting arithmetic operation into gate logic. Now, go ahead.
So kind of like how the binary that you showed us how to add is kind of how the switches would work, essentially. Right. So this 101 plus 110 is the same, translate to how the gate would pass the logic?
Yes.
Yeah.
Yep. So the gates are basically performing the operations. It's performing the map. In other words, you give it the input, it will give you the carry and also the result of the half addition. And then you can combine 2 half additions into a full addition, which is 1 column in the text representation.
Okay. And so higher level source code then translates to the gates.
Eventually. Yeah, that's a long road.
Oh, okay.
We are really
right.
just talking about how to add 2 numbers. But yes, that really that's the most fundamental part of a processor is how do we do computations, right? Most other computations eventually can boil down to subtraction, addition, or comparison, and then conditional branches. And that's why this is so important, because it is the foundation of all the other operations.
Okay, so I just came from Fox's class, and C out, that means something, that keeps running through my head. What is that C out?
It's the output carry. It's the carry to the next digit.
From the adder.
From an adder, yep. So C out in this case, is, when you deal with this column here, this column can contribute a carry of 1 to the more significant bit, right? The one that is to its left-hand side. And that becomes C1, and that's this C out here. This C out is feeding in as C1. And that's why, is that okay? Now, I can claim that this works all day long, but until we actually see it working, my word doesn't hold water, right? So let's go ahead and try it. For those of you who have taken classes from me already, you know that you cannot trust me for saying, oh, okay, this is going to work. Well, maybe it will work. Yep.
R0 and R1. Where is R0 and R1 again?
Say again?
R0 and R1 circuit?
R0 and R1 are invisible because they are inside a full adder. So you have to look into the full adder, because a full adder has 2 half adders. The intermediate results R0 and R1, they're only visible inside a full adder. So when you look at it as 2 half adders, then you can see the wire that connects the half adders together. And the R0 and R1 is basically one of those wires connecting a half adder to the next half adder. But since this picture here is only looking at a full adder, that's why it's not visible anymore. That's a good question. Yeah. All right. right, so let's see how this works. And this is really the cool part, because this tool, TK Gate, is not really just a documentation tool where you can draw gates, make connections and stuff like that. It's also a simulation tool, okay? And that part I think is really, really cool, because you can go to simulate and say begin simulation. So once you begin simulation, you can see these things have changed. Before it's kind of like a darker pink color. Now they're yellow. So, and you can flip the switches too, okay? And well, it's not running yet. I have to click this button here to actually start running. So you can see that if I make changes here, the LEDs would actually start to change. If you want to capture the output of the wires that do not have any LEDs attached to it, you can do so. Okay, you can basically say, I want to insert a probe here and look at how this line is changing over time, and you can actually see how the carry flag is propagated from the least significant bit to the more significant bit. Because each gate takes a certain amount of time to get updated. When you switch or change the state of the input, the output changes after a certain amount of time. It's measured in nanoseconds, but nonetheless, there's a certain amount of time. So if you go to the other window, for those of you who are interested, when you go to this window, it allows you to monitor how those lines are changing states, and so you can actually see the propagational delay of the gates as the full adder works. So in this case, I'm not going to display the trace lines, but I do want to verify that the addition is working correctly. So what I'll do is I'm going to go like this first, because now the switches are all in the off position, which means they are quote-unquote zeros. Okay, so we have 0, 0 as the first number, 0, 0 as the second number. What is the result of 0, 0 plus 0, 0 in binary?
0,
0, 0. So when you look at the 2 bits representing the output as LEDs, they're both off. So we are referring to this LED and this LED here, and they're both off. Okay, seems to work. If I turn on one of the least significant bit, let's say it becomes 0, 1 plus 0, 0, what do you think should be the output? 0, 1, because anything plus 0 is that something. So I turn on just one of them, and then the output is just 0, 1. It works. What about 0, 1 plus 0, 1? What is the output of 0, 1 plus 0, 1 in binary?
1, 0.
It becomes 1, 0. Okay, it becomes 1, 0. So let's go ahead and give it a try, and sure enough, it becomes 1, 0. So it does work, okay? And I think this is a really great tool for those of you who want to kind of look into gate logic a little bit more than what we covered in the past. We will use this tool again, okay? Because there are what we call flags in the processor, and those flags are important because it is not really just reflecting how addition is implemented. This is really just showing you how addition is implemented at the most primitive level. But the other flags are also useful because they are accessible by software, and that's actually how you make an assembly language program. Make a decision. Okay, should I continue execution with the next instruction, or should I branch to somewhere else to continue execution? They only depend on flags, and that's why flags are so important. In this case, we have one single flag as the output, which is our carry flag here. If the input or the result of the addition cannot be stored as a 2-bit number, then the carry flag will be set. It will be turned on. So give me an example, of 2 bits adding 2 bits where the output, where the result cannot be represented by 2 bits. 1, 0 plus 1, 0. Okay, so let's flip all the least significant bits to 0 and flip all the most significant bits to 1s, and see what happens here. The carry flag is a 1, which means the value that we want to represent cannot be represented by 2 bits, but the 2 bits of the results are both zeros, because the output is technically 1, 0, 0 as 3 bits. Okay. Are there any questions? To extend this, it's not too hard. You just you do have to kind of learn how to use the tool. You just do a right click and simulation first, because when it's in simulation mode, you cannot make any changes. And then you just say make And then the module, and you make a module instance. And the module instance that we want to add is an adder. You click OK. Now we have a full adder here. You just need to drag the full adder. No, I want to drag it around. There we go. And then you can also draw. You can also draw the wires. You can make it go somewhere. You can also make a junction. Right click, and then you say Add Wire Segment. That gives you a junction, and that gives you an additional line that you can make connections to somewhere else. But I dragged the wrong part of the line. That's why it's complaining. And obviously we have undo as well. For anything that I do not really want to do. So are there any questions about this little tool? Okay. No questions about this? Okay, I just want to show it to you, to kind of relate this to what we talked about on the other day. We can do a half subtractor too, and then from two half subtractors, we can do a full subtractor, and then the full subtractor will perform the subtraction of one column of binary subtraction. And subtractions are actually more useful because from subtraction, we can also implement comparison. So that's actually a very useful operation. All right, so I'm going to stop the TK gate demonstration at this point. For those of you who are interested, we can continue this discussion at the lab. So you can ask me questions, or you can play with it if you have the latest version of the ISO image, my live distribution, or if you want to play with it on your own distribution. The package name is just TK gate. And it's one of the really kind of lightweight, simple program to use, and I would say it's fairly intuitive too. You just have to spend about an hour or so to get used to the user interaction environment, user interaction standard. It's a little bit different from most other programs, but it's still not too bad. All right. Are there any questions regarding your homework assignment? There should be some questions right about now. Yep.
You don't actually need to make a home directory of our last name. We just target the folder inside of our last name to make it.
Okay.
Data, right?
So let me show you, what you need to do, and I will show you, what your tar file is supposed to look like too. Okay, so that's a good question. It won't take me a whole lot of time to do that part. So I'm going to do my own homework assignment. And this is one of the very few times where I can do my homework assignment before the due date, because it's really just a procedure kind of thing, and there's no real coding involved. So we'll go ahead and go to my homework environment right there. And I'm going to do the whole thing here. Okay. Unfortunately, I have an account under my name already, but that's okay. We can certainly accommodate that.
You can make tag one.
Hmm?
You can make tag one.
You can make tag, yeah. Oyon, remember it's last name. It's
Yeah.
last name.
Wait,
Okay. And do I use? Yeah. Okay. So I'm going to do this part, using my. I'm just going to do the whole thing here. Add user, Oyon1. Okay. So it's going to create the whole thing. Give it a password. Okay. All right. So now I have the account already created. Moving on to the next step here is to install these packages. Now these packages are installed already, so I don't have to install it. But if you're using the virtual machine that I distribute with the disk file, on Moodle, then you'll have to go through the installation too, because it's not already installed in the virtual machine. So in this case, it's already installed. I don't have anything else to do. The rest of the steps do not require administrative access, so I'm going to log out as root and then log in as my homework user. Now in this case, it's kind of harder to do that because my login session is through the GUI, so I can't really just log out without affecting everything else, like the screen recorder, the browser, and stuff like that. So I'm just going to cheat here a little bit and use SU to switch user. Okay, and that's, by the way, that's also what SU stands for, switch user. So I'm going to SU to Oyon1, and then do a CD, to the home folder of Oyon1. Then I'll execute this command here, and I'll cheat so that you guys will ask the question. So I just copy and paste my command here. Okay, it's not pasting. Maybe I forgot to, forgot to copy first. There we go. Okay, mkdir. So I'm just, breezing along here by copying and pasting the commands, not even knowing what they mean. Because like most people, when I see something highlighted, I just say, okay, copy and paste, and run it. And I'm just ignoring everything else that is not highlighted, right?
It doesn't work for virtual machine.
It doesn't work in the virtual machine. That's because you're not, in the home folder of the user that you just created. If you're anywhere else, you do not have permission to create a folder.
No, copy paste doesn't work.
Copy and paste, yes. Okay, that's the question I was waiting for. Well, we haven't really gotten to the painful part yet, so maybe I will talk about it when we get to the really painful part. Okay? Because right now we're just copying commands and there are no special symbols whatsoever. We're just kind of typing along. So it's not painful enough to, to really have to raise your hand and ask, Tag, how do I copy and paste? It's not quite there yet, right? So we'll wait a little bit until we get to that point. Okay, so the next one is to change the directory to the assignment one folder, and that's where I am at this point. Now you have to look at the command prompt because the command prompt is actually quite useful. The first part of it tells you which user you're logging in as, what is the host name. Now host name is not quite useful because we all use the same host name unless you're running it on your own machine. Yep.
Move the command prompt up a little bit.
Oh, okay, because
It's like one line on the screen. Yeah.
there we go.
Thank you.
Okay. See, we should have this class in Rave Hall. But don't tell the dean because next time he will schedule it in Rave Hall and then we'll have 200 students. The exact state students will be here. It has happened before. It's not like it has not happened. Okay, getting back to the command prompt here, the first part of the prompt tells you a lot of information. It's really quite useful. The first part, let me just highlight the part that I'm talking about here. The first part here tells you which user, what is the current user. That's the first part. The second part tells you the host name. And in this case, the host name is Deb Live, for Debian Live distribution. It's not useful for your homework purposes, because you're just working with, most of you are working on a virtual machine. But on the other hand, if you are a system administrator, it is really useful because I open up like easily 10 of these terminals in order to do my work. So I need to know which terminal is open on which machine, so I know what I'm doing, right? And sometimes when I don't pay attention, I'll end up doing something that is not only stupid, but also very devastating. Okay? Because when I run virtual machines too. Okay, I run virtual machines, just to test something, or to do something that I don't need to do to the actual machine. So typically, when I want to shut down the virtual machine, I just say, SU to root, power off, and properly shut down the virtual machine, which is good. One day I log in as root on the power server, did something, and then I go, okay, I'm done here. Instead of just logging out, I do my usual thing, power up, and I was root at the time. So the server did shut down, and that server, let's count how many people are actually using it as we speak. So let's see, go to. Reachable from here? No, it's not. Never mind. Oh, it is. Okay, it's just a little bit slow. Okay, so we'll do a word count of ls/home pipe to wc. So right now we have 288 accounts only for web students. Okay, and then on top of that we have cisp 323 and cisp 400 students. Okay, so I would say approximately maybe around 400 students or so. And I shut down the server because I typed power off in the wrong terminal without looking which host I was on at the time. The fortunate thing was it was 1 or 2 a.m. already, so nobody actually noticed. I sent an email immediately to Walter and said, turn on the server as soon as you get here. And nobody seemed to notice, so that kind of went unnoticed, which is good.
Power off.
Sorry?
Power off.
Power off.
You are going to type power off.
Oh, since I didn't log in as root, typing power off is not going to do anything. Well, it does do something. It will send an email to myself as the administrator to say that, hey, this user tried to do something that he's not supposed to do. And I think some people actually try that, accidentally, do a sudo, blah, 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 and it got reported to me. The system actually reports that to me automatically. So anyway, getting back to our discussion here. Okay, this part here tells you where you are. It tells you what is your current working directory, or the CWD. Now that is important because you don't want to run certain commands at the wrong place. Like if you create the file, your source file, at the wrong place, your directory structure will be kind of messed up, and I would not be able to find your source files, and it would create problems for grading purposes. So it tells me that I am in my home folder. See the tilde symbol here is the home folder. It represents the home folder. So I'm one level down from a home folder as a subfolder. It is called assignment 1. The next step is here to create a program as indicated in the pink area. So this is where the painful part starts, right? Because wow, there's all this stuff here that we're supposed to type. So what are we going to do? Well, if you're running it inside a regular terminal like PuTTY, you will be able to copy and paste. Okay, if you have SSH already established, you can actually use Notepad, whatever editor you want to use. Well, okay, I take it back. Notepad is not going to work because the end of file notation is different between DOS and Unix. But for the most part, we want to learn how to do copy and paste, right? So in this case, I can do it, okay? And this is also a neat trick. Well, this is one half of a neat trick, okay? You will need the other half later on. So I'm going to copy this part first, select and copy, switch to my terminal here, and the command I'm going to do is called cat. So we say cat greater than, and what is the name? ASGN1, I think, .s. There we go. And then we just press the enter key, and then people will say, ha, tag, it didn't work. Well, it's not supposed to do the entire thing. This is only one half of the trick, or 1/3 of the trick, I should say. What it's doing right now is the cat program stands for concatenation. Its only job is to concatenate files. Take a whole bunch of input files, concatenate everything, and create the output file. I did not specify anything at all. I did not specify the input file. I did not specify the output file. If I don't specify anything, it's taking standard in as the input file, it's taking standard out as the output file. How many people are familiar with the concept of standard in and standard out? Okay, that's not encouraging. Standard in is the quote-unquote default input to a program. So unless you do something about it, it corresponds to the keyboard, okay? User interaction, the keyboard of a command line program. Standard out corresponds to the console, which is what you're seeing here in the text console. It's just the output right here. I didn't specify the output or the input, so the input is still from the keyboard. The output, on the other hand, because of the greater than symbol here, it is redirected to a file. In other words, whatever cat is supposed to output is no longer displayed in the console. Instead, it is captured by a file. In this case, the file is called asgn1.s. Okay? So that means I still have to type, right? But remember, I got the text already selected and copied into my clipboard. So now I just have to go here and go to edit and say paste and press the enter key. Okay, this is all great, but how do we stop it, right? Control-C will stop it, but if you do a Control-C, it may not save the file correctly. So the proper way to stop this is well, you're pretty close. It's Control-D. Control-D in Unix land stands for end of file. So you're basically indicating this is the end of standard in, and cat understands when I encounter the end of file of the input, I'm done. So it would exit. So if I type Control D right now on the keyboard, it will stop the cat program, and the file will be created at this point. Yep.
So is that like, because I actually, when you do the program at the beginning, there's AS, I think. If you press enter, it's doing that, it'll log it into that, and I couldn't
Yes.
have that. I didn't know.
That's because the assembler works exactly the same way. If you don't tell it which file is the input source file, it would assume that's standard in. It's expecting you to type the program, and it will do the assembly as you type. Yep. Okay. All right. So, but this is only 2/3 of the trick, because most of you cannot do this, with the virtual machine console, right? Because there's no way you can copy and paste into that thing. That means what you need to do is to use PuTTY in order to, do a paste. Yep.
I think you can also do copy and pasting into it if you actually install the VMware tools that it's
Okay.
asked you to with the yellow thing.
Right.
But PuTTY's much easier.
PuTTY is just, it's also, very useful too. So the way to use PuTTY is like this. I cannot demonstrate it here because I'm not in Windows right now, and I don't have a VMware player installed in Linux. So the way you do it, you might want to write it down in case. Well, you don't have to write it down because I'm talking about it and it's getting recorded, but it's really annoying when you have to find that 1 minute section within an 80-minute lecture just to find out how to turn on that feature. So you might want to write it down, or write down at least the time into the class so you can locate that portion in the video later on. So what you want to do is to go to the VMware settings, go to the network card specification, change it from NAT mode, NAT, which stands for Network Address Translation, to bridge mode. Okay, turn it to bridge mode. You turn it to bridge mode, you save the configuration. It doesn't happen right away. So you need to switch to the root account and reboot your virtual machine. After it reboots, then everything should be good. It should be in bridge mode. Now before you do that, especially when you work in the lab, you might want to change the password of all of the accounts. Okay, so you want to use PASSWD as a command. If you run it as root, you can change the password of all the accounts, or of any account. So you want to use PASSWD as a command name to change the account of at least root, user, and also make sure that your personal account has a reasonable password. Because what bridge mode does is it will expose your virtual machine to the host's actual network. Does everybody understand what I'm saying? Yeah. Which means
But
once you do the bridge mode.
But if you have like a local address, 192, it doesn't help.
Right, if you're home
Yeah.
and assuming you can trust people on your local area
Okay.
network,
Okay.
yes, then you'll be okay. If you do this in our lab, then that means everybody on the same subnet at least can see your virtual machine on the network. And since we all use the same default password for user and also root, they now can just poke your IP address and say, okay, let me see if I can find you. And as soon as they find you, they will log in as user. And if you don't change the root password, they will ask you to root. And then bad things may happen, depending on who hacked into your account. Okay, yep.
Okay, for example, if my information, like from my last name is LV, all my information is in LV, and they don't know the password for my LV, how will they get into my folder?
Because root can go anywhere.
Really?
Yes.
But if they don't know, see, if I have to go from root to my own folder, like my own user profile, I have to I don't have to SU to LV, and then for many SU to LV, they don't ask for a password.
Root can access anything without changing to your username.
But if they don't know my password?
So, but the default user still has a default user password. So you have to change that first, and then you change the root password.
So you change the root password by just pressing PASWD?
Yes, PASSWD. When you run it as root, you can. If you run it by itself, it changes the password of the account that you run it in. But if you run it as root, you can also say PASSWD space user. Then it will use it. You can use it to change the password of the user account. It can be used to change the password of any account.
So So, but if I'm running in root right now, then I only need to write the PA SSWD and nothing else.
Correct. Yep. Okay. So after you do that, there's one more step that you have to do. You have to run the command. You can actually run it as a regular user too. If you run it as a regular user, you have to use /bin/first. If you run it as root, you just run the command ifconfig. Because what it does is it tells you your IP address. So right now we have an IP address here, which is 165, 196, 100, and 104. Which reminds me that I need to change my password as soon as possible too. So let's hope that I can type faster than some of you. Yes, I'm safe. Okay. I'm actually relatively safe because you guys can only access the wireless. There's only one plug here, and the wireless cannot get back into this subnet like this. So the 100 subnet is only exposed to other machines that are currently on the wired network. If you go in to the wireless, you cannot come back in through to the same subnet. So I'm actually relatively safe unless Carol's class is doing something funky, then they can actually see me.
What can we do from virtual machine?
Huh?
From virtual machine we cannot do anything anyway.
If someone hacks into your virtual machine,
Yeah. You can delete it.
they can delete stuff. Yeah.
That's it.
They can install the backdoor and use it some other time. They can do whatever they want to do, like it is a real machine. It's just that it's easier for you to kind of disable it and restore from another image. But you should really treat it as a real process, as a real machine. Because you don't want your virtual machine to become a part of a botnet, right? Because that's what it can become. It's a part of it's a botnet. Become a part of a botnet. Sorry?
But you could just close the virtual machine and recreate it from a backup.
Correct. If you find that there's a problem.
Oh.
All right. Okay, so once you have the IP address, after you switch to bridge mode, you find the IP address. Then you can use PuTTY to go into that to use that IP address as the destination. SSH is already installed, so you don't have to worry about that part. So you just use PuTTY or WinSCP, depending on whether you want to do file transfer or just open up a terminal. Yep, go ahead.
Also, is it safe from attack over the internet if you do this, or is it only possible from local area network?
When you turn on bridge mode, it becomes visible to your local subnet. So if you're behind a firewall to begin with, then your virtual machine is invisible from the other side, unless you set it up, port forwarding to that particular IP address.
If you have a router, it's
If you have a router, you have to turn on port forwarding to even expose anything. If you put the IP address of the virtual machine into the DMZ, you're on your own. The DMZ stands for the demilitarized zone, which means you're not inside the firewall anymore. So if you put your virtual machine out there, not within the firewall, then it will be exposed to everything on the internet. Well, this one has it doesn't have much surface installed. The only thing that is exposed is port 22, which is SSH. So it's relatively secure. All right, so that's basically the whole trick. I did not demonstrate the second part because I'm not running a VMware player right now. So if you have any questions about that step, you can go to the lab and I can show you, how to do that. Okay, so let's go ahead and finish this homework assignment. I'm almost done here. I just need to copy and paste a few commands. And of course, I don't really have to copy and paste because I know these commands. So I think cisp310 asgn1.o, asgn1.s. Okay, so this is also a good time to kind of explain what this command is actually doing.
And it's different for 64-bit.
Is different?
Just.
Oh, you have to specify. Yeah, I included your link, the link to your blog to the whole class. So in this case, AS is the command. It stands for assembler. G stabs, is an option, to the assembler, which means I want to retain the symbol tables. Okay, it's for debugging purposes. -O specifies the output file, so it is always followed by a file name. In this case, asgn1.o is the name of the object file name, and asgn1.s is the name of the source file. So when you press the enter key, it will do its job. Unless something is wrong, it won't give you any type of output. But you can use ls-l to take a look here, and I have no idea why it's called nah. That's. Oh, you know what? I know what it is. Okay. Does anyone speak a foreign language? Okay. Does anyone recognize this as your native language? I did not set my language pack correctly, and that's why it's the name of the month. It stands for February. And obviously the time is way off too, because I didn't set my time zone correctly. So if you want to set the time zone, this is also a kind of like a good discussion too. If you want to set the time zone, the way to do it, I'm doing it here so you can actually you can replay this part here. If you do it in Debian, the way to do it is dpkg reconfigure tz data, time zone data. And once you do that, it will just ask you, please select the geographical area where you live in the US, and then you just go to Pacific. And now the time zone should be set correctly. So when I use date, it's still using the wrong language. That's a separate issue. I cannot remember the code name for the US. It has to do with the startup, the kernel startup code. I just set it up incorrectly. It's the locale that is set up incorrectly.
It's either EN-US or US-EN.
Yeah, I got that part set up incorrectly. That's why it's not using English right here. All right, so let's get back here. Okay, so moving on to the next command. The next command is ld, which is our linker. So you say ld-o. That once again, -o specifies the name of the output file. And asgn1.o is the only input file in this case to the linker. Press the enter key. Unless something is wrong, it's not going to do anything. It doesn't print anything. But when you do a ls-l, once again, we now have a new file. And you can even tell from the timestamp of the files which one is created first, which one is created second, and which one is created last. So asgn1 without an extension is kind of green too. Okay. That's a highlighting to let you know it is an executable. The other two are not executables. So as an executable, you can just run it using /asgn1, which is the name of the file. It runs it. It says hello world, but that's not your homework assignment. Your home. Sorry. ASGN1. No, that's the .s1 is the source file. This is the actual executable. This is the executable. And you can see the executable is pretty small too. It's 876 bytes. Okay, it's not big. All right, so let's go through the entire command here, or your entire homework assignment. Okay, this is the part where these are commands to the debugger, to GDB. So what we are doing is we are storing all of these into a file. So we go back to the command prompt here, and we are going to create the other file. The other file is supposed to be called what? Debug.gdb. So we'll say debug.gdb, and then once again I just paste and press the enter key, because Control D doesn't work unless we are at the very beginning of a line. Now that we are at the beginning of a line, we press Control D, it gets out of the cat program. And if you do an ls, we have the debug script here. And now we just run gdb asgn1. This is a redirect to the standard in. So we are feeding it all the debugger commands. This is redirection to the output. So instead of printing everything, now if you forget about this step here, it will just print all the output to the standard out. So that's why you can see it. But when you put the redirect here, everything will be captured by the file called debug.log. and it doesn't show anything. But when you do a ls-l, now we have one additional file, which is debug.log. Okay, that's the log file of the debug session. Okay, we're almost there. We still have to create the tar.gz file and then upload it. To create the tar.gz file, you are supposed to run this rather long command, like this one. If you can copy and paste, it's great. If you cannot, I'll spell out exactly what you have to type. Okay. Okay. So the command goes like tar C for create, Z for using gzip compression, V for verbose. Okay, so it shows you what files are getting compressed. Sorry. Okay, it's verbose, and then F is the extension to tell the tar command what is the name of the output file. The output file is tilde, which means home, and assignment1.tar.gz. The extension tar.gz is by convention. Unlike DOS and Windows, Linux does not really make use of file extensions much. It's really for human beings only. Okay, so if you name it incorrectly, it is still a tar.gz file, and tar would still be able to handle it. It's just that it is not conventional if you use any other extension. And also, my script is going to be looking for this particular file name. And then you specify a space and then a dash uppercase C. What this does, and combined with a slash, is it's basically saying when it is about to do the compression and the archiving, switch the current working directory to the root of the entire file system. That's why it's a dash C uppercase C for changing the current working directory. Okay. And then the last part is the most confusing part, because it is a backtick, which is at the upper left-hand corner of your keyboard. It's the back quote. Sorry?
Usually with the tilde.
Yeah, it's usually with the tilde. It's the non-shifted version of that key. And then PWD. PWD stands for print working directory. So what this does is, if you run PWD by itself, it prints the working directory, which is basically slash. At this point, it's going to be /home/audio1/assignment1. That's my That's the output of PWD. So instead of asking you to hand type the entire current working directory, this command is doing it for you. So you cannot make mistakes when you're doing that. And as a result, when you run this command, it is looking from the perspective of the root of the entire system, but it's only archiving this particular folder. So when you press the enter key, this is the expected output. Removing leading slash from member names is correct. Okay, that is not a problem. Okay, so this is the output that you should see when you run the tar command. And now the tar command, the tar file is created. You just have to upload it to Moodle. And since I just talked about how to make your virtual machine visible to WinSCP, you can use WinSCP, FileZilla, or whatever to copy it to the host machine and then upload it to Moodle. Yep.
What was the Z standing for again?
Z stands for gzip. It's a compression algorithm. Yep. There are a few compression algorithms that are known to tar. The other extension that we do not use in this class is using J, which is bzip. But we're using gzip, which uses Z as the code. Yep.
What's the host name for the WinZip for the ARC? What we will have I think it's a host name, right? For the
Host name of
for the for the server.
for what purpose?
For when you go to WinZip, they ask you for that, right?
WinZip?
Oh, the WinSCP.
WinSCP.
Yeah.
WinSCP is on Power. If you go to power.arc.lostreels.edu, there's a link to it.
The Power, right?
Yep.
Instead of using keyblock command, can you put in your own customized directories, just in case if you're not on your
Okay, let me give you this one. Okay, you can check for yourself. Okay, you can check for yourself. So let me do a CD here, which puts me back into my home folder. So you might want to do this before you turn in your file, is to run this command. Say tar, and then tzvf, in this case, T stands for test. Okay, so it's only testing. It's not expanding. It's not compressing. It's not creating. It's just testing an archive. Okay, so I'm going to test my archive right now, and your output should look similar to this. Obviously, it's not going to be all in one. Substitute that with your own last name, but that should be the output when you run your tar tzbf on your own tar.gz file. If it is not this, if it is not home/your last name and then assignment 1, as the prefix of everything else, then you have to do it again and make sure that it looks like this. The reason why that is the case is because I look at this path to find out who turned in that homework assignment. That's how I can ID you. Yep.
Oh, so you just, I don't actually have to use, I don't have to make my user that I can just target that file structure.
Well, if you don't tar in a particular way, you cannot really embed this as a part of your path if that is not a part of your folder structure.
Yeah. So if you had a user and just made a folder with your last name and just worked through that folder,
I use relative path.
You can, well, okay, in that case, you would have to, in your user account, you would have to create home/your last name, and then inside that folder, create assignment 1 and do everything inside assignment 1. But then you have to be careful about what to use when you run the tar command, because you have to make sure that the result of the tar command creates a path that looks like this. So there are ways to kind of get around this without creating your own account using your last name. But I think just creating your account using your own last name is just easier. Yep.
Your untar command though only looks for our last name first, and then it unzips it, or it strips everything away but the last name and the following directory, because that's the folder structure. Correct?
It creates the home subfolder too. This is the whole thing that I'm expecting from your homework assignment. Come on, this is a programming class. We surely can deal with archive files and getting archived in the right way.
Just use your name.
Yep. Go ahead.
Does it make sense to install browser on the virtual machine? Does it make sense to install browser on the virtual machine?
Okay, here's the question. Does it make sense to install a browser on your virtual machine? In order to install a browser on your virtual machine, you're going to suck in, X window and a whole bunch of other stuff, and the disk image is not big enough for that.
So it requires X-Min. Because if I try to install like Chromium, it doesn't work. It requires like graphics.
Because it wants to suck in a whole bunch of stuff, to get the graphical user environment to work. You can do it if you expand the size of the disk, and you can probably do it if you're running VMware the non-player version. That's probably an option. You can do it offline, and then you have to do a resize E2FS to resize the actual file system. Because if you just make the disk larger, it doesn't make the file system recognize the entire space. So you'll have to run, resize E2FS to make that work. So it's got to be a little bit of work to get that working. Yep.
So does your breaking script look for the username on the actual archive itself, or does it look for the username in the files that are
in the path?
Okay.
In the path. So what I do is I will run the command to locate, all of the asgn1.s, the source code file. So I will look for all of those, and my script will tell me, okay, I found this file under this particular folder path. So I will visually, myself, I will visually go through that path to locate the last name, so I know who turned in that particular file.
Okay, thank you.
Mm-hmm. Yep.
If we want to do something different with our directory structure, can we just use symlinks to make it look like that?
As long as when it expands, it looks like that, it's good. So if you use symlinks, you want to make sure that when it expands, it looks like that.
Okay.
Because tar has specific switches to deal with symlinks. Whether a symlink remains as a symlink or whether it's actually followed. So you have to select the right option for symlink handling.
Okay.
Yep. Any other questions? No other questions? This is all good? All right. So once the homework assignment thing is out of the scope here, we will continue. Did anyone buy that book, the textbook, the PDF? $11?
I actually bought
The printed version? All right. All right, so we are moving on to, we are done with, half adding and full adding. Basically that's, basically the earlier discussion. But we'll go ahead and just go in and make sure that we cover all of the topics. So we have the full adder here. I use the math symbol, for all and stuff like that, but it's really still saying the same thing as what we talked about earlier today. Implicit carry flag. This is where things get really kind of dirty and kind of complicated. It has to do with the way we do things. If we just implement an adder using the traditional full adder design, that means we have a full adder here. Remember the inputs to a full adder. You have one input from one bit of one number, one bit from the other number as inputs. And then you also have a carry coming from the less significant digit, in this case on the right-hand side. The output of a full adder is one resulting bit and a carry going to the more significant bit on the other side. So in theory, you can just make instances of full adders and expand it to 32-bit, 64-bit, or whatever width you want to deal with when you're adding numbers. So let's just go ahead and expand it maybe 3 times. Okay. So this becomes the carry flag into the next full adder. The next full adder is taking 2 inputs from the 2 numbers that we are trying to add. It's creating one output, which is a part of the sum. And once again, we have we daisy chain this whole thing. So input, input, output, and so on. We'll just deal with 3 bits here. The problem with this approach is there's a propagational delay. In other words, every time, if you just look at an AND gate here, every time the input changes state, it takes a certain amount of time. We talked about this a little bit earlier. It takes some nanoseconds for the output to be correct, to stabilize, to basically reflect the correct result. But remember, this is really only a small part of a half adder. And we need 2 half adders to make a full adder. So that means by the time we get to here and also here, it's going to take a little bit of time. Now, if you daisy chain this, that means in order for the entire number to make sense, you have to wait for the propagation delay all the way from here, all the way to bit 31, or if you have a 64-bit architecture, to bit 63. Okay. Now, bits are numbered like array indexes, so the least significant bit is called bit 0, and that's why we count to 31 and 63 respectively. Are we doing okay so far with that concept? Well, if you do it this way, your adder is going to be quite slow because it has to wait until everything has settled down and is one chain. There's nothing you can do to speed it up. Is that making any sense? So the only way to get around this problem is not to use the propagational delay, and instead we're going to use the logic equations. So in other words, in order to compute the carry flag of something else, we're going to do a combinational type of expression instead of using a daisy chain to do it. The nice thing is, it will significantly speed up your half adder, your adding logic. But the bad thing is, the logic gets fairly complicated. This bit, okay, this equation here is representing this bit here. And it's already a little bit complicated. Okay, I'm pretty sure it can be simplified a little bit, okay? But you can imagine what it looks like by the time you get to bit 31. Because bit 31 is going to make use of, okay, in this nomenclature, this is x0, y0, x1, y1. Those are the 4 bits to serve as the input to compute S1 here. Are we doing okay so far? So you can imagine what it looks like when we have everything all the way up here. This is bit 31 of the sum. It's going to make use of x0 all the way up to x31, y0 all the way up to y31. And I'm not going to do that. I'm not going to come up with the equation to do all that stuff. So when you work for Intel, who is going to do it? Exactly, it's automated. Okay, that part is automated. But I do want to point out, this mechanism, because this is why the Intel processor is not just, halting when you say add. It's not just saying, okay, hold on a second here. I'm waiting for the carry flag to propagate throughout the entire thing. Because it's just making use of all the input bits. It's not even using carry propagation at all to get to the final result. Now, there is a compromise you can do, okay? In other words, instead of making, the adder so complicated, what you can do is you can bunch things together. So instead of having a full, full speed 32-bit adder, you can make 4 full speed 8-bit adders. And that will still significantly improve the propagational delay because now you only have to propagate 3 times to finish the entire thing instead of 32 times to finish the entire thing. So there are ways to kind of trade off, between how much silicon you want to spend as opposed to how much performance you want to get out of the processor. All right, so that is that. And optimization of a full adder for 2 bits. We are looking at the input and the output because with a 2-bit by 2-bit adder, we have 2 bits. These are the least significant bits of the input. These are the most significant bits of the input. This is the sum, the output of the first bit, sum of the second bit, and these are the carry flags. This one is not useful, but this one is useful. So it's a full table of the expected output of the entire thing. And when you get into electrical engineering or computer engineering, they have specific techniques to look at a truth table like this and make it as simple as possible. Okay, since I'm not teaching that class, I'm just going to leave it as such. And I think that might be a little optimizing technique here. Unfortunately, I'm not going to teach this part of gate logic optimization. You will encounter this in your computer engineering classes to optimize gate logic. And it's really cool stuff. I wrote all of this stuff, so at one point I actually know it. All right. So after all these discussions, how far have we gone in terms of explaining the architecture of a computer? Well, let's take a look at a picture. Okay, I think this picture will kind of give you an idea of how far we have gone. We have just talked about how to add 2 binary numbers. Okay, so let's see, where we are talking about, how much stuff we have talked about inside the processor itself. And this is another program that I think you guys should really look into. And this one, there's no excuse not to play with it. Okay, it's called Not Johnny Cash. It's a Johnny Simulator. Okay. This one is kind of cool too. I really like this kind of projects. All right, so we'll take a look at a screenshot of this program. This is a typical screenshot of Johnny when it's running. Okay, it shows you quote unquote a simulated computer system, not just the processor, but also including memory as well. And it's really cool because this is a Windows program. So I actually have to use Wine to run it in Linux. But for those of you who run Windows natively, it's just a Windows application. 32-bit, no big deal, nothing tricky about it at all. Wine runs it actually fairly well. I mean, it's really easy to run. What we have done so far is this little box here. See that little box that says plus? That's what we have done so far in terms of specifying something in gate logic. Okay, the rest we haven't even touched on yet. Okay, so we are really at the core of the entire processor because the processor is basically the control unit combined with the ALU or the arithmetic logic unit. That's that portion is your what we call the processor inside the computer system. So we are really at the core part of the processor itself, and inside the ALU, this is really the most important part of the ALU. This is where computation actually happens. The rest of it, the accumulator is really just a little notepad, to write down, answers. Okay. These other things, the green stuff here is called a bus. Basically a bus is a whole bunch of bits that can move from one place to another place, so to transmit information. So we have only touched on this part here out of the entire processor. From time to time, I will come back to Johnny. I will actually get it installed and run it in class, okay? Because it really gives you a pretty good idea of how a processor works. Okay, how does it hook up to the memory bus? How do we execute instructions? Okay, how do we get an instruction in, and how do we decode it? And once we decode an instruction, it consists of micro steps. In other words, really, really small individual steps. And in Johnny, you can actually perform those steps one by one individually, just by clicking on each thing that can be clicked. So we'll definitely get to that part again, when we talk about the architecture. So we're going to stop I'm going to stop the lecture at this point. But for those of you who are interested, definitely download Johnny and just kind of play with it. It comes with programs already. And you can also kind of experience what it feels like when you have to program a computer using machine code. So I will go to the lab later. If you have any questions about the homework assignment, or you just want me to kind of check your submission, we can do that over at the lab today. And I forgot to take roll. It's okay. I'm not going to ask you guys to stay just to take roll.